Hi there, this is the second part of my M62 series, and today we made quite a few changes. First of all, most mainly, is I got a haircut and trim my beard, and also I have defined the memory map a little better, and which I will show you right here. And you'll notice now the top two banks are selectable with the bank addressing system, and also I have proven the bank addressing system, which I'll be showing you shortly. And further on in the video I'll be discussing the 16-bit I/O operations, which I thought was something that doesn't really happen on the Z80, but it turns out it does, and it's actually documented in the datasheet. So yeah, and also I'll be doing a little bit on a power on reset circuit, which I have added. And so without further ado, let's get to the bench and have a look at this this banking. Okay. Now you see I've extended the main board here. I've added LEDs for the bank addressing. This is bit 0 to bit 7, and this is the I/O request line. It's an active low, but the LED will light on when it's active, so it's an inverted light. And there's a jumper here to turn it on and off. Well, you know, I'm going to be replacing this card soon with this, which I still haven't finished yet because I wanted to prove this circuit first. I'm just going to turn it off for a minute and I will show you. It currently resides here on the memory card because the Z80 card is just full right now. These 4 chips are what it consists of. There's 2 PLDs used for address decoding. Not only does it address decode to allow you to write to these 2 chips, it also address decodes so when you are reading from the correct memory address, it will present which of these to the bank address bus. So like if it was bank 0, bank 2 area, then it would put the stuff in the register of this chip to the bank address. If it was in bank 3 area, then it would do for this chip. Currently, bank 3 is not wired up yet. I wanted to make sure bank 2 works. Bank 3 will work definitely. I just have to do it. Look at that, just caught a mosquito. Very nice. Second one of the season. Okay, and I put the schematic online for those that want to see it. Why is that not focusing? Come on. Doesn't want to focus. But anyway, I'll overlay the numbers for you on the screen. The 2 PLDs are ATF 16V8Bs from Atmel, and the 2 logic chips, which I think is showing. These are 373s, even though the diagram I actually have 573s, 74 series. The 573s just have the inputs on the one side and the outputs on the other side. These have them one either side. Okay. And you'll also notice I have these stands on here. This is kind of what it's supposed to look like. It's more like a mock-up of how it's going to look. Unfortunately, these stands are very warped. I'm hoping to get some better ones printed this week. But for now, it works. You know, it allows me to slide these in. So there we go. Okay, so let's get on with the demonstration. Actually, I'm going to remove the processor card. You see the This is where I was going to put the circuit, but there's just not really enough room on it. So, but on the final, in the next revision of that card, it will have it in there. Alright, let's... Right. It's really a pain, you can't really see those LEDs too well with that, the light directly above. Okay, so it's all on, and basically to write to the bank addressing, we're gonna do an IO address 00000, which is all zeros right now, and let's set a data pattern. So 2 on, 2 off, 2 on, 2 off. Let's do that. I really wish this would keep in focus. Okay, and then I'm going to do. I'm going to trigger the IO request. Okay. I know I'm not hitting right now to do it, because right now it doesn't listen to the read and write commands for the IO. It's something that I'm going to fix eventually, but it doesn't matter right now. So now turn these off. Okay, so anything above 8,000 to BFFF is bank 2. What is that? I'm having trouble focusing. Right. So I've set the address to 8,000, 80000F, and I'm going to do a memory read. And as you can see, on the bank address bus is the value that I set, which is good. So if I go to the next bank, the one I haven't wired up yet, and I do a read, this doesn't activate or do anything. Only when I'm in this bank. See, I'm just going to put some random on, and there. See? Now we're in that bank, so come on. But yeah, so that's proven, so I'm all happy about that. That means we can start, you know, I can I can finalize the memory bank memory addressing for now, so I'm all happy with that. And I also did the oh yeah, I'm hitting the reset button to show you the power on reset. Well, can't really see that. You'll see that in a minute actually, or in a little while when I show you the captures for that. I've also got my logic analyzer set up. This plugs in to there, and that's how I was able to capture the diagrams of what I'm going to be showing you. So yeah, and so yeah, I'll go to my main bench to explain how we'd be using the bank addressing in the program in itself. Okay, now as you see here, we have the memory map the way I've got it right now, and what happens, individual memory cards will do their own address decoding. This is so it'll be as flexible as possible. Say it may have some weird memory configuration on a card, this will allow it to do that. This is what I'm going with right now. This may change in the future for the second revision. I don't know, we haven't fully figured it out yet. But anyway, this is how it is. We're separated into 3 banks, and the top 2 banks, bank 2 and bank 3, are individually addressable with 256 selectable, well, sub-banks, I should say. This is where the big problem is. There's these banks, and then there's these banks, so it's I really should think this through a bit further before finalising the standard. But we'll call these sub-banks for now. So it's the card's responsibility to decode this address. So if it knows it's in bank 2, then what it'll do, it will also look at the bank address bus, and it'll either address decode that itself or recognise the well, that is address decoding it. It will decode the bank address as well, and it will select the appropriate bank on its card or sub-bank on the card associated with the bank address. And the way the bank address circuitry is designed, if the bank 2 address is on the address bus and the memory request line is selected, then the bank 2's register will show its contents on the bank address bus. Same with the bank 3, but I don't have that wired up yet. So basically you have a card. Oh, that's not it. You have a card, obviously with a bigger connector on it, and the address range is set for bank 2. Right, bank 2. And let's just say we have the sub-bank select back to 0, 1. So if we do a if we want to write or read to this card, and let's say this card is at the beginning of bank 0, so it's at 8000 and bank 1. So we want to talk to the memory on this card. The first thing we do is we do an I/O output to 0000. Yes, this is using 16-bit I/O, which I'll discuss that in the next section. You'll see. So I won't go into detail. This isn't an actual command or mnemonic right now. It actually takes about 2 or 3 commands to achieve this. So basically we want to output at this address, we want to do the bank address, which is this, right? So this number then goes into the bank address register for bank 2, and then basically you want to basically read or write to the address so we'll read load address load port load the accumulator from 8000. So now what will happen is 8000 will arrive on the address bus. The memory request line will go high, sorry, low, because it's active low. The bank addressing decoding will see that we're in bank 2, and it will then put this number onto the bank address bus itself. Then this card will then simultaneously see that we're looking at the address 8000 and bank address 01, which matches itself. So therefore it selects the correct portion of memory and pushes that out onto the data bus, and then therefore that goes into the accumulator. So it's a bit like a normal read of memory, except we've got an extra 8 bits for the address in a way. So it's kind of like having a 24-bit address bus, but it isn't, because the way the banking is. But for all read and write operations for down here, it's just going to be normal. And if these are all if these are banks selected as 0, 0, then these will be normal as well. Normally we'd only have to set the bank if we're going to be dealing with a different selectable bank or sub bank from that point on. So like we can load 0, 1 into bank 2's register, and this will be set to sub bank 0, 0, 1 until we change it. And therefore we do any normal read and write, it will be expecting to be talking to subbank 01 at that address. Kind of hope that explains it okay, because it is a bit of a weird concept. Okay, I thought I should I cover a little bit about the stack pointer, since I don't think I explained it too well in my last episode. Now, I didn't really explain what it was used for. Well, I said it was used for jumps and well, interrupts, but that bit of text was cut off, unfortunately. So I'm going to explain it now before I continue on. Now, the stack pointer is a register in the Z80 processor. It is it's a 16 bits wide because it points to a location in memory, which addresses are 16 bits wide in the Z80. Now, and it basically just points to the stack. Now, what the stack is a place where the processor has pieces of information shoved in there, so you can retrieve them again later. And the stack pointer then basically just says, okay, we're going to put the stack like here. Normally you put this at the very top of your RAM, and the stack itself, it grows downwards rather than upwards. So I like to use, in this case, because the way my banks are set up, between 4000 and 7FFF for the RAM. So I like to put my stack pointer to 7FFF, which is the RAM top. So 7FFF here. And then if you do a jump, the processor will then push the address you're jumping from onto the stack and decrement the stack pointer down one, so it then points to the next address. And then when it returns from that jump, it will then pop the stack, which means it'll take the lowermost piece of information off the stack. Now, you can think of the stack a bit like it's like if you go into McDonald's or a Burger King, and when you get a soft drink, you will see their cups, they're all pushed into a little round receptacle at the back behind the counter. Basically they load the cups in, so the last cup that goes in is the first cup that comes out. It's pretty much the same concept as a stack pointer, or maybe even the stack of plates at an all-you-can-eat buffet, the spring-loaded ones. It's the same concept. It's a last-in, first-out buffer, as they call it. And you can also push registers into the stack and then pop them out again afterwards when you're done. There is commands for that, push and pop, and it's used to store registers before you enter a subroutine, and that way when you come back out you can restore the registers back to how you want, but you have to handle that bit. But the processor uses it to handle return addresses. So basically that's what it is. Now, the reason you see in my code that I always define it at the beginning, even though I'm not doing any jumps, or well, I do a jump, but I'm not doing a jump to subroutine, which is where it's really used. If it's jumping to a subroutine, then it really needs to use the stack for that. But I've been playing around with the NMI, non-maskable interrupt, and the first thing the non-maskable interrupt does when you trigger it is it will put the current address on the stack, because interrupts are subroutines that you return from. Even though I haven't been doing it, but it still needs a stack for that. And if you don't define the stack is defined at 0000. Lots of strange things happen. It's unpredictable, but I found there's been lots of problems with it. My last time I played around with Z80 stuff, I kind of forgot to put the the stack pointer code in, and I kept wondering why none of my jumps would ever work. Well, that's why. I hope this this helps with the explanation. I've been doing a fair bit of research with the I/O interface on the Z80 processor. I've always found that people have been using the address bus on the Z80 for the I/O. They've been using just the bottom 8 bits. I was always hearing that you can use the top 8 bits, but nobody does. So I decided to do some research into that, and as you can see, I got my logic analyzer hooked up. Now, I can't rename these labels, unfortunately. These are the groupings for the of the address. So that's the first 8 bits of the address, second 8 bits of the address, and that's the data bus. And then I put some lines. Now, unfortunately, when I captured this myself in my lab, I used I have the refresh shown. Usually it says with run length encoding, the very last bit is always going to be low. So I'm assuming they're using run length encoding when they save the file, because I've lost that information. So, it's you are going to see a lot of addresses showing up that do not make sense. It's because it's part of the refresh cycle, and there's no way I can gate that out so it doesn't show. The concept is, I was trying to figure out how to push the the upper data bus, the upper 8 bits of the data address bus, and I can never figure out exactly how to do that. Now, if I start my Z80 simulator here, I find it doesn't have any support for using the top 8 bits of the address bus, so that's a bit of a shame. It's not like it's an undocumented feature. It is actually a documented feature. So if I use the I/O ports editor, you see it's only got 8-bit addressing, so which is a bit of an oversight if you ask me for the program, but fair enough. And I always thought that it was some sort of undocumented structure that allows you to use the upper 8 bits, but no, if we refer to the datasheet itself, and I'm looking at the outC operation here, it says clearly right here, the contents of the B register are placed on the top half of the address bus at this time. So this is normal. This is supposed to happen. So what I've done is I set up a bit of test code, and I told it to so I'll show you the test code. Where is it? So here we go. So I've loaded the accumulator with 4D ASCII M as usual, and it's the only ASCII character I remember. So I loaded the accumulator with 4D, the B register with 55 because it creates that nice off-on pattern, the C register with AA, which creates the on-off pattern, so an inverse, and output 4D to support the number that's in the contents of C. So what should happen is on the address bus we should see 4D, on the lower half of the address bus, on the data bus we should see 4D. On the lower half of the address bus we should see AA. On the upper half of the address bus we should see 55. And what I've done here, I got this looping so it's constantly running it, so I could pick it up in my capture if needed. I also set up NMI to do the same thing, but I haven't used it in this thing, this part, and obviously I set up stack pointer again. Okay, so let's look back at the logic sniff. Right, this line here you see is the the trigger point. I don't know, does it tell me what I triggered on? Oh yes, I told it to trigger on okay, I told it to trigger on the refresh being high, M1 being low, reset being high, and 25 and reading at the address 0000. So that's what it's come up with here. So if we follow it along, we can look at the M1. Maybe I should make this window a little bit. Actually, I should this way. Are we seeing okay? Yeah. Oh, okay. So now we see the M1. So it's going to fetch from 0000, and it fetches 31. Which is the first opcode here. We should do that there. So it fetches the first opcode, and we go along. This here must be part of the refresh stuff. But from 001 we retrieve FF, and 002 we retrieve 7F, so that's doing good. So let's see. So we keep going. So we're loading the accumulator here with 4D. Then we're loading B with 55. Loading C with AA. And ED, so it's an extended instruction here for ED, and instruction 79, which will be which is the out port mentioning C at the contents of A. And so then if we look carefully, see here, now we have a write on the I/O line, and on the data bus we have 4D. Lower address bus is AA. Yeah, that's correct, because we're doing support C. So it's AA, and then 55 appears on the upper address bus as stated here, because 55 has gone into B. So this proves this is exactly as it should be, which I'd be very confused if it wasn't. Okay, so I decided to do some research and to include a power on reset circuit. I also got feedback about this, so that's one reason why I went into research for it. I cannot remember the location where I got the original little bit of snippet from. Basically just using the 555 as a single shot circuit, so they're you find them everywhere, so it's not based on one source. Now the 555 single shot circuit here, the way it's wired up, it's pretty much, it's almost the same as the one over here, except it's not being able to be re-triggered because it's designed to come on and be triggered once when the system starts up. Maybe I could hook up the reset line to here to make it do that. I'm not sure, I haven't experimented with that yet, I haven't thought about it until just now. But anyway, I will explain how this is all set up here. Now this is my ever-evolving design for the Z80 board. So I've got the single step circuit here. I'm experimenting with the bank decoding logic here, which I'm going to be changing again soon. Okay, so basically what I have is I had two Schmitt triggers taking the reset line to basically condition the signal as before, and I thought, okay, I just OR the positive output here in between these two Schmitt triggers to you know, say whether the reset from the bus is triggering it or the reset from the power on is triggering it. And well, using De Morgan's law and some other Boolean algebra stuff, I basically come up with this using a NAND, which is already on the board. I could just stick it here between the two Schmitt triggers, and this works. I actually have it on the board. I'll show you a picture of that in a minute. I'm not actually in my lab right now. I'm doing some post commentary on the my editing machine. You notice this is a 556, not a 555, because it's 55 to dual 555 basically, and this is the single step circuit. So, you know, might as well use it all from one chip rather than two separate chips. But, okay, so so yeah, basically the power comes on and it resets the circuit. This oops, sorry, my scroll wheel is a bit dirty on my mouse. Now this is an RC network here, and I think it was 100 milliseconds. I can't remember. I'll show you a diagram in a minute of how long it is. Anyway, so basically the output goes high for the 100 milliseconds and then goes low again. So and it basically, because it inverts, it's it just resets it once. It pulls it low basically here for the 100 milliseconds and it still accepts a normal reset pulse. So that's the circuit as is. Okay, so I will show you. I built it on the breadboard and this is what I come up with. I put a 100 nanofarad capacitor here, and there's the 1 meg, was it 1.5? I can't remember now. Oh, it's the 1 meg, yeah, it's a 1 meg resistor. And these clips actually go to my logic analyzer. Right, so the black one is ground. I got some power coming in. Black is ground, and the white one actually goes to the plus 5 volts because I'm going to trigger off that. And the green is going to the reset line. Nope, sorry, green is the output. This is it's not inverted, so it's going to pulse high. I will show you the logic capture. Now I don't have, well, my oscilloscope is it's not a storage oscilloscope, so I can't capture waveforms or you know, store any waveforms on it, so I can check all this. So I use my logic analyzer to do this. But you see here, this is where it triggered. See when the power line comes on, when I turn the power on, then we see this here, the output goes high, and then 11.811 milliseconds it goes low again, and then it doesn't do anything till you restart the circuit. Now that is with the 100 nanofarad capacitor. Now I put two of them in parallel, the 200 nanofarad, and it pretty much doubled the delay to 223 milliseconds. So if the pulse width isn't wide enough for what I want, then I can just add another capacitor in parallel. So I will show you now what it looks like on the board. I fitted an OR gate here and the 555 timer here. This diode and this resistor, I was experimenting with different ways of introducing it into the reset line. I didn't want to use an OR gate. I wanted to try and save on a chip, and well, it didn't work. I tried to use diode, make a diode OR gate, but it just for some reason wouldn't work. I could probably done it with transistors, but yeah. So anyway, so yeah, here's the top side of it. I can enable it and disable it from here, and here's the bottom side. And so yeah, here's the 555 timer. Here's the OR gate, and here is the 100 nanofarad capacitor. Yep, and obviously the resistors on top as a through hole. Now this here is the Schmitt trigger circuit. This comes in from the bus. It's the reset line from the bus. It gets inverted, and they used to be joined here, so it'd invert again and then go to the processor, so to condition it. But I broke the connection between the two. It was just a solder blob. So now this goes off here to one of the inputs. But yeah, I got the wires mixed. Yeah, goes off here to one of the inputs of the OR gate. The other input comes from the single shot circuit. And then the output goes back over here, back to the second inverter, Schmitt trigger inverter, and that seems to work fine. Right here I have the jumper, so I could take it in and out of the circuit when I was testing it, and got here remnants of like the resistor and the diodes and stuff still that are on there. Now this is only a 555 on this board, but the obviously it would work exactly the same with a 556. So yeah, so I did a little testing with it. It does appear to be much more stable, and it doesn't affect the circuit negatively. Once it's already started up, it all works great. But yeah, so that is the power on reset. Okay, thanks for watching. I hope the information today was informative and helped a bit. And as always, you can always find more information on my website, which I will show and put a link below in. And also, all my up-to-date schematics will be available in the link shown as well. And I'm constantly updating them throughout the week and making changes here and there. And also check out the blog style of the website. I always add to the end of that exactly what I'm doing, or what I'm experimenting on, or what's new, and eventually it gets translated into the main information page. But for now, thank you for watching, and I'll see you again soon. Goodbye. Thank you very much for watching my video. And if you like what I do and wish to contribute to me, please visit my donations page or consider supporting me through Patreon. I'd like to say thank you to those that have donated, and I'd like to shout out to my patrons, Without your help, this wouldn't be possible. Thank you very much.